So it's my pleasure to introduce today's speaker, Volodymyr Mnih. So Vlad was an undergrad here at U of T. That's when I first got to know him. We did a project together with my then PhD student, Mnih, and it was a fun project. They were, I don't know if you remember this, Vlad, but they had a camera set up, and they walked around King's College Circle and took some photos, and then had to learn the map and learn localization. So it was like very early days for cameras and learning the environment. Then he went on and did a master's at Alberta, came back here and did his PhD with Jeff Hinton. And has since then, I think, been at DeepMind, and has done great work at DeepMind. He's well known for the work on learning video games, on work on attention and reinforcement learning. So he's become a real star in the field of machine learning. So very happy to have him here, and welcome, Vlad.
Thanks, Rich. Yeah, it's great to be back in Toronto. Can everyone hear me, by the way? Okay, so today I'm going to talk about some recent work that's we've been doing at DeepMind on efficient multitask deep RL. And this has been joint work with a lot of great colleagues, but I should say Lasse Espeholt and Hubert Sawyer really led this project and carried it forward. Okay, so why is deep reinforcement learning exciting? I think I want to, make maybe a somewhat controversial argument that I think is just obviously the right framework for trying to get to artificial intelligence. So why is this the case? So there's probably no one agreed upon definition of what intelligence is or what artificial intelligence means, but I think one that I like is trying to build machines that are good at sequential decision-making problems faced by humans. So I think the sequential decision-making aspect is crucial. Perception, of course, is important, but really the crux of intelligence is sequential decision-making. So reinforcement learning comes in because it gives us a general framework for doing learning in sequential decision-making problems. So there are fields like planning, but if we want to learn in sequential decision-making problems, I think RL is really the right framework and maybe even the only one. So where does deep learning come in? Hopefully I don't have to defend this in Toronto too much, but if we're looking at problems faced by humans, then the most obvious way is we'll need some way to perceive the world. And currently, deep learning is, I guess, the dominant approach to doing perception. So vision, speech, and slowly catching up in language. But I think more generally, deep learning is just a framework for doing end-to-end learning and deep computational graphs. And if we want to do deep RL, then okay, maybe we don't have to learn the perception through reinforcement learning. But we'll still need to deal with deep computational graphs because as soon as we're looking at time and sequential problems, there's an aspect of thinking time. So intelligent agents will have to balance how much time they spend thinking about a decision. And I think there's just no getting away from dealing with deep computational graphs. And deep RL is just the study of how to put these together in a way that works well. A quick look at progress in deep RL. So probably the two most well-known benchmarks right now are Atari games, so this well-known set of 57 Atari games, and the game of Go. So if we look at the performance of the original DQN architecture from, I think, 2015, 2013, it achieved something like 75% median human normalized performance over these 57 games. So what this means is that on half the games, it achieved more than 75% of the human score, roughly. And then if we look at various extensions and new models that people have proposed for Atari, the improvements have been quite dramatic. So the median human normalized score on this benchmark has almost doubled every year since then. And now this anonymous submission to iClear is well over 400%. So this is really quite amazing. And if we look at the game of Go, then we see sort of the red bars show the best agents before DeepRL. And then we see sort of a progression of improvements from incorporating RL, from the original AlphaGo, which defeated the European champion, so with ELO about 3,000. And within the span of 2 years, we basically see the latest AlphaGo, which essentially just does reinforcement learning and does not use human data. The ELO is just way beyond any human player. So in just 2 years, we've seen this dramatic progress. This is exciting because, okay, for many interesting problems, we can already build machines that learn and achieve performance way better than humans. So what's the next step? Okay, the title kind of gives it away. But humans aren't just good at any one particular thing. So as impressive as AlphaGo is, it maybe still is nowhere near the abilities of a toddler. Because a toddler can do many things, maybe not particularly well, but can still walk and maybe show basic language abilities and stack blocks, something that's still maybe beyond current best learning methods. So what's missing is basically general agents that are able to do well across many tasks simultaneously. And I think this is why looking at multitask deep reinforcement learning is important. So the architectures might be entirely different and we might need entirely new learning methods. But I think this is really the right time to start putting a lot of effort into multitask RL, because single task performance is really basically reaching very high levels in a lot of the domains people use. So this talk will be basically about an architecture that has developed a DeepMind over the past year or so. And I'll start by talking about some challenges involved in doing multitask DeepRL, and then talk briefly about the DeepRL architectures we've been using for single task training, like DQN and A3C in particular, and look at why maybe they're not that well suited to the multitask setting. And then I'll present the new architecture. So what are the challenges in doing multitask DeepRL? So let's say we want to start off simple and just consider many tasks in one coherent visual world. So we're going to spend a lot of time looking at the DeepMind Lab 3D environment. So let's say we want to go beyond training an algorithm on a single task to training an algorithm and the same set of weights to be good on, say, 20 or 30 tasks at the same time. So one immediate challenge is data efficiency. So methods like DQN and A3C and all the state-of-the-art DeepRL methods might use something like 200 million frames of experience to learn an Atari game, and our best methods on the 3D environments typically trained for maybe 1 billion frames to learn to navigate random mazes or something like that. So if that's just for one task and we want to go to 30, we can't just take 30 times more data and 30 times longer to train. Because if it takes, one or several days to do one task, we're looking at months to learn, say, 30 tasks. So that's really not going to work. Another issue is stability. So some methods are quite stable in the sense that on the Atari games, we're actually able to train a single algorithm with the same fixed hyperparameters to play all the games. So you train it on each game separately, but everything, including the learning rate, is fixed. Other methods are less stable. So if we want to look at, again, learning many tasks at once, maybe sensitivity to hyperparameters will be an issue. And specifically, the methods that work well on 3D domains currently tend to be the ones that are more sensitive to hyperparameter settings. Another issue is scale. So the networks that are typically used in DeepRL are actually quite small by today's deep learning standards, so maybe 1 million free weights to learn. But again, that's for one task. So will we need networks that are 30 times bigger? It's not clear, but most likely we will need more complicated architectures. And then maybe they will be even slower to train. And the last one is potentially task interference. So continual learning with neural nets is still a big open problem. When you train on one task and then move on to another one, there tends to be catastrophic interference. So will there be issues in just putting the knowledge for doing 30 tasks into a single network? So I guess the next little bit will be basically about a quick overview of DQN and A3C, which have been our workhorse DeepRL methods at DeepMind. And I'll start with a bit of basic RL, but hopefully we won't need too much. So again, we're looking at the standard reinforcement learning setting where we have an agent that interacts with an environment over discrete time steps. So at time t, the agent takes an action, which is given to the environment, and in return, the agent receives a reward and the next state or observation of the next state. And the goal of the agent is to optimize the future discounted rewards. So a key quantity that pops up everywhere in reinforcement learning is what's known as an action value function. So if we have a policy, which is a mapping from states to actions, the value of action A in state S is the expected future discounted reward for following the policy from this state if you took action A. So what's nice about it is that it decomposes recursively, and you can express the value of action A in state S with respect to the values of the successor states that you can get to from state S. And this is what's known as the Bellman equation. So the math maybe isn't that important, but intuitively, the action value of A in state S is simply telling us how much reward are you going to get if you take action A and then follow your policy. So, of course, we're interested in acting optimally. So you can define this notion of an optimal value function, which is simply the maximal achievable value where you maximize over all possible policies. So in Markov decision processes, there is a unique optimal value function, and you can get an optimal policy by basically taking the action with the highest value in each state. And the optimal policy isn't necessarily unique because multiple actions can be optimal. So what's nice about the optimal value function is that it also decomposes according to a Bellman equation, where if you want to act optimally in state S, you basically just need to know the rewards you will get for the different actions, and then the optimal value function at the successor states. So how does this help us? Well, there is basically this famous key learning algorithm, which uses the Bellman equation for optimal action value functions to give us a learning algorithm. So we start off with guesses for the value of each action in each state, and then we just interact with the environment, taking actions in some way, So most of the time you might want to take the best action according to your current estimate of the value, optimal value function, and with some probability you will take a random action. So Q-learning applies updates based on the Bellman equation, which essentially brings your current estimate of the value of the current state closer to the target given by the Bellman equation. What's amazing about Q-learning is that under some relatively mild conditions, it is guaranteed to converge to the optimal value function Q star. So this means we basically already in some way have the right algorithm for solving a lot of interesting problems. The challenge, of course, lies in how you parameterize your action value function Q. So DQN, the method introduced by DeepMind in 2015, is basically based on the idea that let's take Q-learning and make it look like supervised learning while using a convolutional neural net to represent the action value function Q. So why do we have to make it look like supervised learning? Well, the problem arises because when we're doing Q-learning, the target for the action value at the current state depends on our estimate of the value of the next state. So if we simply take steps in the environment and do updates to our value function, you end up with a very non-stationary learning signal. So if you end up getting stuck in some part of the environment, you'll do a lot of updates on these states. And then when you move on to the next part, then maybe those updates will basically undo the learning you did in the first part. So again, this is the problem of catastrophic interference. When we learn with neural networks, we typically want a fixed data set and we sample data points IID. So what DQN does is tries to slow down Q-learning to make it look as much as possible like supervised learning. So now the idea is, okay, we will do mini-batch SGD optimization of the Q-learning objective, but we will not do it online in the sense that we won't do the updates on the data that we just got from the environment. We will simply act in the environment and put all our experience into a giant buffer known as the replay buffer. And then we will sample mini-batches from this buffer and do updates on that. So because all the data goes into this giant buffer, it will change slowly as you move through different parts of the environment. And the updates you will make will be basically much more stable and much more evenly distributed across your environment. And the other trick that was important in stabilizing Q-learning with neural nets is also fixing the targets, the weights used to compute the target. So again, the target for the current Q value depends on the Q value at the next state. So we basically take some set of weights and fix them to be the weights used to compute the targets. And we keep them fixed for some number of updates, maybe several thousand. And during the time that these weights are fixed, this is essentially supervised learning. We sample data from this data set, and we do regression towards these targets. And every so often, we take the latest weights and swap them into the target network to get the knowledge from the recent experience. So as we saw on an earlier slide, DPN was able to reach ballpark human level performance on the Atari domain. And since then, it's been applied to other problems. And I guess our experience using DQN has shown that it has certain pros and cons. So probably its main advantage is its stability. So from the start, we were using fixed hyperparameters across all games, which is nice if we want to learn many tasks at once. DQN is also GPU friendly, so we were learning on GPUs from the beginning. So even though the networks used on Atari are quite small and don't make the best use of GPUs, if we want to use larger networks for other tasks, the GPU will do the work. Probably the main issue with DQN type approaches or other mini-batch Q-learning approaches of this form is that they tend to be slow. So training DQN in one Atari game, 200 million frames, takes about maybe a week on a modern GPU. So that's not great if we want to learn on many tasks. And another disadvantage is that we found that they are not as easy to combine with recurrent neural networks. So if we want to learn in 3D environments which are partially observable, we'll need some way of building up a state representation over time. This is not a major disadvantage. It has mostly to do with the fact that to do experience replay with recurrent nets, you need some way of storing the old states of your RNN. And they might become stale over time, and basically it's a bit trickier than with other approaches. So that's DQN. So the other class of reinforcement learning methods are known as policy gradient methods. So here the idea is to say, okay, well, our goal is to get as much reward as possible. So we actually have an objective, which is our expected future reward. So can we just optimize it directly with gradient descent? Because we know gradient descent works really well. So it turns out that there is a way of doing this efficiently. So the policy gradient theorem says that the gradient of this objective is just the expectation of the gradient of your log policy multiplied by the action value function at that state for that action. So that's a very useful expression, but it says, okay, we need to know what the optimal action, well, not the optimal, but we need to know the action value function for our policy. But it turns out that there is a very easy sample-based approximation. We can just do a Monte Carlo sample-based approximation and get a very practical algorithm. So the way it works is you run your policy and sample a trajectory of states and actions, and you get some return. And you just approximate the gradient using this one sample. So the return is actually an unbiased estimate of the action value for your policy. So basically we can just take gradient steps like this. And this method is known as reinforce, and it's been known since the late 80s or early 90s. So if we wanted to combine it with DQN, we would be in a bit of trouble because DQN does experience replay. So when you sample data from your replay buffer, it doesn't come from your current policy distribution. And for that gradient to be unbiased, it has to be a sample from your current policy. So we did some work a few years ago in scaling up this approach of policy gradients by simply saying, okay, what we can do is just use parallelism to get around this problem. So we'll have many agents interacting with different copies of the environment, and each one will basically run the policy in the environment, compute an estimate, use the sample-based policy gradient estimate, and update some shared copy of the weights. So initially we were doing this on one machine and the workers were different threads, and the model was stored in shared memory. More recently, we've been looking at distributed setups where you might have a parameter server and communicate over the network. So the overall method where we combine this asynchronous training of agents with policy gradients, or at least one particularly successful combination is called A3C, or the Asynchronous Advantage Actor Critic. It essentially does this reinforce update, but it also subtracts the value of the current state, which is basically just a variance reduction technique. So it does not change the fact that the gradient is unbiased. And instead of using the full return, you let the agent play for some number of steps, use the rewards you got during that time, and then truncate, add an estimate of the future reward from that point on to get an estimate of the queue. So that's the overall approach. And it also has some advantages and disadvantages. The main one is probably its generality. So A3C worked especially, well, it worked quite well on Atari, but it was also easy to combine with recurrent nets, so it worked well on these partially observable 3D environments. And it was also trivial to extend to continuous control. So if we want to look at multitask RL, this might be a good starting point. It was also fast, so because we could run many workers at once, we could train much faster than DQN, and it surpassed the performance of DQN on Atari in 16 hours or something like that. So this is a pretty huge speed up in terms of training time. Yeah, as I mentioned, it's quite friendly to using RNNs. It was reasonably stable in the sense that for the on the Atari domain, we showed that it does work with fixed hyperparameters, but it is more sensitive to the hyperparameters than DQN. So if you tune the hyperparameters like learning rate, you could get even better results. So in practice, people tend to do a lot of, well, do big hyperparameter searches with these methods. So the method is somewhat scalable in the sense that on one machine, we can run as many learners as we have threads. But to use big networks and use more learners, we have to go to the distributed setting. And there is a point after which adding more workers doesn't really help anymore, and the data efficiency starts to suffer. This is because in asynchronous gradient descent, if the gradients are stale, they might actually end up hurting your overall performance as you add more and more workers. And finally, there haven't been very good combinations of A3C which used GPUs. And if we want to use bigger networks, this is basically essential. Okay, so what's the best way forward here? So at the start of this project, we decided that scaling up A3C was the most likely approach to work well for multitask RL, because we were looking at these 3D domains and the method already worked well. So the question is basically, what's the right way to go about scaling this up? So in a distributed training setup, as I already mentioned, just adding more actor learners doesn't work that well, because as you add more and more of them, the gradients might become more and more stale, and there might be more and more contention on the centralized parameter server. But of course, it's nice that we can collect more and more experience by adding more actors. And for, sorry.
What's a stale gradient? What do you mean by stale gradient?
So the stale, right, good. The question is, what is a stale gradient? So basically, each actor gets a copy of the parameters. It runs the network forward. And then when it's collected enough rewards, it computes the gradient, which is, of course, with respect to the parameters that it has. And then it sends the gradients back to the parameter server. By the time they arrive, the parameter server may have applied updates from other learners. So it will have a different set of weights than the ones that the actor computed the gradient with respect to. So if the staleness is high enough, then the best thing might be to actually throw it away. It might not be useful anymore. But again, the nice thing about the distributed setup is that it's very scalable for collecting a lot of experience. And if we want to learn on many tasks at once, this seems like something we want to do. But what we want to avoid is communicating gradients, because that doesn't seem to be as scalable. Okay, so what's a better way to do this? So the overall setup that we ended up going with is something like this, where we end up switching to a centralized learner and many distributed actors. So now the way it works is each actor still asks for the parameters and then starts executing the policy in the environment. But when it's collected enough rewards, it basically just sends the observations to the learner and not the gradients. So the nice thing about this is, okay, the actor now is only doing inference, so it's not computing gradients. So it's doing half the work, so they can go about twice as fast. And the learner now basically gets all the data. And the learner can now use a GPU and it can parallelize as much of the computation as possible. Of course, doing this well is still tricky. So how can we make this setup efficient? So the reason that this is difficult really boils down to the fact that in many environments, the time it takes to execute a single step in the environment can be highly variable. So for example, in these 3D environments, taking a step means rendering the next observation. And that depends on how many objects are in the scene. And especially in procedurally generated environments, there might be steps where you're generating a new maze or something like that, or you have to load new meshes. And basically, these transitions can take even longer. So naive ways of parallelizing A2C, or just the advantage actor-critic method, don't really work well. Probably the simplest method is to say, okay, we're going to roll n environments into one, and we're going to go step by step. So we will tell all the actors to run one step in the environment and wait for the data to arrive, and then run the next step. So this is really bad because each step will be as slow as the slowest actor. And as you add more and more actors, it becomes more and more likely that one of them will be going through one of these slow transitions. So this is, basically this is not workable in these 3D environments. It might work reasonably well in something like Atari, where the environment is essentially free. But scaling up to richer domains, it's not really workable. So a slightly better way to do this is to let each environment, again, execute a trajectory, and then just wait for all the trajectories to arrive. So now it's not that each step is as slow as the step of the slowest actor, it's that you basically have to wait for the slowest actor, but the time it takes to run the whole trajectory. So this ends up being slightly more efficient, but you still end up with many idle workers. So what's the best way to do this? So the most efficient way to do this sort of setup involves decoupling the backwards pass. So what we have now is basically all the actors just generate, they get the current parameters and they generate a trajectory of observations and rewards, and then they put them into a queue and send them to the centralized learner. And the learner just continuously dequeues big batches of trajectories and does learning on those. So the reason that the key challenge in making this actually work is that By the time the observations get to the learner, you may have already changed the weights of the policy. It won't be necessarily a big change because it might be 1 or 2 or 3 mini-batch updates. But it turns out that that's enough to actually harm your method. If you do just on-policy, policy gradient, the weights lagging behind, or the experience coming from a slightly older version of the policy, will lead to bad updates. It will harm learning. So the trick is, if we want to make this work, we need to be able to do off-policy, policy gradient updates on this slightly stale data. And it might seem like, okay, isn't this the same problem? In the asynchronous SGD case, we had stale gradients, and now we have stale experience. But dealing with stale gradients is hard. It's really not clear what to do with the stale gradient. You can apply it, you can throw it away, but it's not clear if there's a way of fixing it. With experience, it's different. It's still a valid experience from the environment, and you can use these off-policy reinforcement learning methods, which are able to improve your current policy based on experience from some other policy. So Q-learning had that property. But to make this work with policy gradients, we need some trick of doing that with policy gradients. But the overall architecture that we're describing here, which is having parallel actors which are off policy in order to do a decoupled backward pass, we're calling a pod architecture. And you could use various different reinforcement learning algorithms instantiated with it. But the particular one we ended up using basically uses this new off-policy policy gradient method. So again, we need some way of correcting for the fact that the policy changed. So we introduced this vtrace policy gradient method. It's basically an application of importance sampling, which corrects for the fact that the policy changed. And it uses several tricks to reduce the variance of the importance sampling correction. So the actual math maybe isn't that important, but the key things to understand is that the importance weights now are between your current policy pi, that's the policy with respect to the current weights on the learn, and experience behavior policy mu, which is basically, these are the probabilities of the actions for the weights that the actor was using. So the actor has to send these probabilities to the learner. And if the learner has access to the probabilities that the actor was using, it can use its current policy to correct for this change. And it might look somewhat scary, but one way to think of it is, okay, if we're in the on-policy case, where pi and mu are the same, and all the importance weights end up being 1, then basically the vtrace corrected estimate for the value is actually exactly, I don't know, I'll try to go back. So if the policies are the same and all the importance weights are 1, then we end up with the same value estimate that we had in A3C. And as the policies drift apart, then it starts correcting the estimate a little bit based on the difference between the estimated value plus the reward that was sampled. So again, this value comes from the current weights on the learner, but the reward was obtained using weights that were on the actor. So adding some of the difference weighted by the importance sampling weights can correct for this. So the importance weights are truncated using at rho bar and C bar. If rho bar and C bar are set to infinity, then this will be an unbiased estimate of the value with respect to the actor's weights, but it will have very high variance. So in practice, you can truncate the importance weights to be at most 1, so then this product will not blow up, and you get a biased estimate, but it has much lower variance. And in practice, this does help with the off-policy drift a fair bit. So now the overall architecture we're proposing is basically a combination of the V-trace advantage actor critic and the pod distributed architecture. So we use this usually one centralized GPU learner, which is using the V-trace advantage actor critic method, and many CPU actors which are collecting experience and sending it to the learner. You could also use multiple GPU learners, but for most of our experiments we were using just one. Okay, moving on to some actual results. So the experiments we did use 2 networks. So one is the standard convolutional neural net LSTM that people have been using on Atari and Labyrinth. So it's a relatively small convnet with 2 convolutional layers and 1 fully connected layer going into an LSTM. And it outputs a policy and a value function. We also did experiments with this deep ResNet, which basically has, I think, 3 ResNet blocks. So it's quite a bit deeper than this network. The reason that this is somewhat unusual is that on most of the domains where DeepRL has been applied, namely Atari and Labyrinth, convnets deeper than this never seem to help, which is really at odds with what we see in supervised learning, where just deeper and deeper ResNets seem to lead to better and better results. So we'll see if we can get some mileage out of a deeper network. So the last thing we can do to really make things go faster is optimize the learner. And this is pretty standard for supervised learning. But now that the learner is doing both the forward and backward pass on the GPU, and it has all the observations and all the rewards, you can do things that you normally wouldn't be able to do in an online setup. So typically in online RL, you can't in parallel compute the convnets for all the observations because the observation at the next time step depends on the action that you output. So you basically have to wait to produce the action in order to get the observation and compute the features. But in this batch centralized learning setup, we have all the observations and all the actions and the rewards. So we can put all the convolutions into a single mini batch. And basically, anytime there is a feed-forward block, we can batch everything over time and really make use of the GPU. So this helps even when the convnet is relatively small. Using a really big batch helps utilize the GPU. And you can also be a bit more clever, which again I think is standard in RNN literature, and parallelize the bits of the LSTM forward pass that only depend on the input. So if you make the entire LSTM forward and backward into a single GPU kernel, you can get even more parallelism. So the first thing to look at is, okay, is this thing fast? So we have 2 sets of benchmarks here. The left one is for the small CNN LSTM architecture. And basically we see, okay, at the top, A3C on a single machine with 32 workers gets about 5,000 to 9,000 frames per second. And this, the variance comes from it basically depends on which level in the 3D environment you're running it on, because some are faster to render. We can also go to a distributed A3C setup where we have a parameter server and many actor learners. So by using 210 CPUs, we can get 55,000 frames per second. But we're going to suffer from some gradient staleness. So there is another GPU implementation of A3C, which is quite similar to our architecture, which was proposed by NVIDIA. It doesn't use distributed actors, I think, and this number isn't fully comparable because they had an older GPU, but basically it's actually in the ballpark of a single machine A3C agent with 32 cores. So then the next two lines are basically the two naive ways of parallelizing A2C that we looked at earlier, and there you can go faster, so you can get to 6,000 to 17,000 frames, depending on the approach. So once we start looking at V8-2C pod, the most compact implementation is a single machine pod, where the batch size is 32 and there are 48 actors. And this gets us to 15,000 to 28,000 frames. And now the limiting factor becomes actually the rendering speed of the environment. So this, the learner could do more work if the environment could be rendered fast enough. So the next line is, if we go to a distributed setup without the optimizations from the previous slide, 150 actors and one GPU learner, we get 80,000 frames per second, which is already noticeably higher than distributed A3C with roughly the same resources. And if we add the batching optimizations and add more workers, we can actually get to 200,000 frames per second, which is a pretty drastic improvement. And then we also have similar but smaller set of results for the deep ResNet. Again, here the distributed A3C gets 16,000 frames per second, and we can go twice as fast with a single learner pod. But of course the question is, okay, it's good that the throughput's better, but how well does it actually learn? So we did a number of experiments on the DM Lab 30 task set. So this is a set of tasks in the DeepMind Lab environment, which will be released basically as a benchmark for multitask RL quite soon. And it consists of 30 levels, each of which is essentially testing some cognitive task. So there are tasks based on grounded language where the agents are given instructions for what to do, like, for example, are all the guitars red? If yes, you go left. If no, you go right. There are memory tasks which require the agent to remember some rewarding part of the environment. There are outdoor foraging tasks in a naturalistic environment, and I think, yeah, there might be close to 10 types of tasks and 30 levels overall. So the first set of experiments was not in the multitask setting. So this is just running these agents on one level at a time. And here we're comparing a single machine A3C, a distributed A3C, and the single machine pod. So here we're showing the amount of data consumed by all the actors on the x-axis. So even though the pod architecture is actually way faster in terms of throughput, it actually also tends to work about the same or better in terms of data efficiency. So this is because it doesn't suffer from the same gradient staleness problem, and the off-policy drift can be corrected. So this is showing that, yes, actually, the V-trace correction does help. What's interesting is that the method VA2C pod is also quite a bit more robust than A3C. So here, this might be hard to see because the text is small and the color is changed. But here we're showing on 5 levels, we ran a hyperparameter sweep for each method, and we sorted the final scores in descending order. And we're basically showing sort of how well you did over the entire set of hyperparameters. So if the curve for one method is above the curve for the other method, it's basically saying across all hyperparameter settings, you're doing better. So there are more hyperparameter settings where the method is as well. So here, again, the VA2C pod is shown in deep blue. So again, on top of being way faster, it's also much more robust. And this is basically confirming now that DQN was robust because it's a batch optimization. It's using a mini batch optimization method instead of stochastic updates like A3C. So it's not a property of Q-learning versus policy gradients. Doing batch optimization with policy gradient methods gets you stability too. So the really, I guess, interesting results are in the multitask setting, because that's what we set out to do in the first place. So what we're showing here is the average human normalized performance over the 30 levels, where it's capped at 100%. So if you're doing better than human on some task, you still only get 100, and it's averaged over all levels. So we see that the A3C multitask implementation basically is the worst performing method. Because not only does it suffer from gradient staleness, it does even worse because any actor at any one time is collecting data from one of the environments. So what ends up happening is on the parameter server, you're getting updates, each of which comes from experience in just a single environment, one of these 30 tasks. So in one task, you might be learning to go one way, and another one, you're going another way, and they're basically, it looks like there's considerable interference. The different pod implementations don't suffer from this because all the actors push the experience into a queue, and when you collect a mini batch, you basically get experience from different tasks. So you can take a bigger step, be more stable in the learning. So the green curve shows a pod architecture which used the shallow convnet. The dark blue one is showing the same, but for the deep ResNet. So I think for the first time, we're seeing considerable gains from using deep ResNets like the ones in supervised learning and DeepRL. And we think the reason is that basically the task is now rich enough to benefit from deeper and richer architectures. A single Atari game, it's enough to learn just a few low-level features to do purely reactive control. Probably the most exciting bit is if we look at the light blue curve. So what that shows is training experts on this task set. So we train a separate pod architecture on each level separately, where the amount of data consumed over all tasks is the same as the multitask pod. So what this is showing is that if we train on all the levels separately and then compute average performance, we actually do worse than training a single model on all the tasks at once. So we are seeing essentially positive transfer learning here. So learning on multiple tasks at once now improves data efficiency, and there isn't actually that much interference from different tasks. So here we again have the colors are the same as the previous plot, but we see results for all 30 tasks separately. And I think the interesting bits come again from comparing the performance of the deep pod with the expert pod architecture. So the levels where the multitask pod outperforms the expert performance often happen to be language tasks, where you have these language tasks with different objects and colors. And it seems like the agent is able to transfer knowledge from one task to the next. There is some negative transfer, for example, these two levels, and they happen to be the naturalistic foraging environments. And this probably makes sense because, as we'll see in the videos, the visuals for these environments are totally different than from the other tasks. So I'll wrap up with videos of the agent. So here the agent is collecting mushrooms in this desert type environment. And again, these are all policies learned in the multitask setting. So this is a relatively easy task. It collects mushrooms, and over time they regrow, and to get optimal performance, it helps to remember where you've collected a lot of mushrooms before. This one I will try to zoom in because it can help to see. So there's usually a question that, for example, are most knife objects red? And if it's yes, the agent goes left. If no, the agent goes right. So any fork sign, anything magenta, any suitcase magenta, most hammer objects. So this is quite nice. So the agent is able to learn some more grounded language knowledge.
We're training those
Sorry.
learner knows
Sorry, this is really. So this is just simple maze navigation where the agent is basically looking for apples, and sometimes it resets, and again it helps to remember the collected apples previously. So in this task, the agent has to basically collect keys of different colors and open doors of different colors to get its reward, which is a popsicle. And yeah, so those are basically all the results. So to conclude, so we have a new distributed RL architecture, which is basically, it achieves very high throughput, but at the same time, the learning is even more stable than in previous distributed approaches. So this agent, even though it was mostly developed for multitask training, it's now probably our most popular agent internally for different tasks. So it works as well on single task RL problems. So synchronous batch is more robust than async SGD. So that's, I think, settled, at least for us, one puzzle, which was why is the stable than D3. And we are using data or environment as a challenge set, and we've already seen some positive transfer, and again, finally seeing networks similar to what's state-of-the-art in supervised learning improve performance in deep RL tasks, which I think is exciting because now it's saying, okay, we have environments that are rich enough to support learning of representations with these deep nets. So yeah, that's all. Thanks for your attention.
For the grounded language environment, raw pixels input, and did you embed the words as vectors?
Yeah, so the question is for the grounded language environment, what was the input like? So yeah, it got pixels, a pixel view of the environment plus a string for the instructions. So the string was passed through an LSTM and then fed into the agent's LSTM. Yeah. I'm sorry, I can't hear. Sort of in 1 minute. Oh yeah, sorry. I think it's basically how does the batching work with LSTMs if the history can come from different classes? So here, I guess the architecture what the environment the training time. So each actor is only interacting with a single environment, and what it sends to the learner includes sort of the previous LSTM state. So each actor sort of maintains a consistent LSTM state, and it just sort of sends the initial state for the enrollment.
Are there any techniques to deal with the catastrophic forgetting power you mentioned initially?
So here we're not doing anything special about it. I guess there is some work on multitask RL where, for example, people learn to, they try to learn the distribution with which to sample tasks. So you might favor some tasks initially and others later. So we're not doing that here, but yeah, the method should be orthogonal. Like, it should be easy to combine. Yes, I think it's Sarah.
Using pre-trained networks for using classical intent at all, did I pre-train on like supervised tasks?
Yeah, so here, yeah, we're not doing any pre-training. So yeah, this was one of the first things we tried with the old CPU. So I think everyone thought, oh, we're going to do unsupervised learning or some supervised pre-training, and things will work better. It's been really, really hard to get any positive benefit from any kind of pre-training. I think there are even results showing that if you train an RL agent on a task and then randomly reset a few of the top layers and then train it on the same task again, this can actually be worse than starting from random weights again, even though you're reusing the same low-level filters. And basically, with reinforcement learning, a lot of the problem comes from exploration. And if you pre-train the weights, you have to be really careful to make sure that the exploration still happens in a meaningful way.
So you mentioned the problem of stale gradients and stale observations.
Yeah.
It seemed that you were dealing with stale observations using how do you detect and extract this information in the policy? How do you detect stale gradients?
Well, we don't. Yeah. So I guess one thing that's in the literature is, I think, asynchronous SGD with backup workers. So supervised learning, you can say, okay, I'll have 150 workers, but I'll wait until I get gradients from 100 of them, and then apply that update and throw away the rest. We briefly considered trying this with reinforcement learning, but because of the way the environments work, we realized it's actually a terrible idea, because the transitions that are slower to render, they're not basically, it's not just uniformly random. They're slower because they're special transitions, like maybe the final state in the environment where you regenerate the map. So basically, yeah, that was the danger. You can look at sort of how many updates were applied between the time you computed the gradient and the time the parameter server got it. But I think in supervised learning, you can use that to throw away old gradients, but in RL, it seems very dangerous because you'll just skew the distribution. So in a sense, maybe changing the policy even. But we haven't actually tried it, so who knows, maybe.
Another question about the multitask and the task transfer. When you look at what kinds of things are actually transferring, like about conversations, about policy, what is actually, how is transferring?
That's hard, yeah. People have been doing some work on this. I guess, yeah, sometimes there's been some positive transfer from just learning an exploration policy. So maybe in the random maze levels, you quickly learn, okay, I should just move around and pick up apples. And then another task where, again, you're in a maze, but you have much sparser rewards. It would have been harder to learn just to move around as much as possible. So there is some, I think, transfer from policies, and yeah, I think there is some work from Raz Salahudinov's group where they specifically pre-train exploration policies like this. But the stuff with language, it seems like basically transfer in the language LSTM, it just learns common word embedding. So that seems to be a major effect too. Yeah.
So there are a number of things that are different between SVC and this new thing. So I guess there you move from using gradients to using observation. You added important something that you got false learning. Probably also decoupled the hyperpath. There are some things in the network. If you are asked to order them, it becomes important. How do you do that?
Oh yeah. So basically, this architecture makes a number of changes to A3C. It's possible to order them by importance. So I think, for me, one key takeaway is that it looks like doing mini-batch optimization in DeepRL is the right way to go. We should forget about purely online. This is just more stable. So even in a different setup, batch or mini-batch seems to be the way to go. So that really helps a lot with stability. The important sampling, So I did have a secret slide which basically shows different importance sampling corrections. So you can compare the green bar means no correction, and this dark blue bar means the V-trace correction, and then there are some simpler alternatives. And you basically see that, okay, sometimes it's fine to be on policy, but then there are some levels where not correcting will just break learning. So there I would say it depends on the task, depends on the number of workers, like how much staleness you have. So those two probably are the main things here. Yeah. So yeah, we're looking at that now, but this is, Atari is interesting, right? It should work, but I feel like it's almost like the transfer that one would hope to see in Atari, I think, is so high level that no agents aren't operating at a level anywhere near understanding that you have a ball in Pong and a ball in Breakout, and that, you know, you're controlling a paddle which is horizontal in one game and vertical in another game. Like, these seem like very obvious parallels to us, but these, I guess, model-free RL methods, they don't try to make sense of the environment. They just try to learn the value function. So there's been some work on multitask on Atari from DeepMind and other places, and I think the transfer has been very limited, and I would say maybe even accidental, that you just happen to get the weights into the right magnitude for learning to start a bit sooner. But I don't expect any sort of high-level transfer using these kinds of approaches there. Maybe some visual features, but yeah, I guess we'll see. I think it's definitely the next thing to try. I don't know if we have more time.
All right, that's it. Thanks a lot for a great talk.
Okay, so next week we have a change.
Oops, there we go. Next week we have a change of pace, so we're going from reinforcement learning to natural language processing. Chris Manning from Stanford will talk next Thursday. And
Lunch as usual outside, thanks to our sponsors,
GM, Scotiabank, and Shopify. See you all next week.